nested quantifiers. We will say that whenever there is a quantifier inside the scope of another quantifier. To make this clear, let us look at the following example. It says that for every x there exists y such that x plus y equals 0. X and y here are real numbers. Now what we are saying here, for every x, a real number, there is another real number y such that if we add them, x and y, we get 0. This simply says for every real number there exists a negative value of that real number. So for every real number x, there exists y such that x plus y is 0, and we know this result is true. So this is an example of what we mean by nested quantifiers. As we see here, there exists y is in the scope, is within the scope of for every x. The existential quantifier is in the scope of the universal quantifier. Okay, to make that clear, let us see more examples. Okay, now in these examples we will take x and y to be real numbers. So the domain consists of all real numbers. Okay, let's see this one. It says for every x and for every y, x plus y equals y plus x. And we know this is true. So for every x and for every y, so that means for every two real numbers, x plus y is the same as y plus x. So this statement says addition in the real numbers is commutative. If I add two real numbers, x and y, it is the same as y plus x. Okay. So we have two universal quantifiers in this example that are nested inside each other. Okay. Example number 2. It says for every x and every y and every z, we have x plus y, let me say it that way. Okay, y plus x. So first we add the last two integers and then we add the resulting to the first, or here it says we add the first two integer and add the resulting to the third one. So does it matter which two integers first we add? It does not, and then we call it associative law holds. And now for every x and every y and every z, this statement is true. So we have three universal quantifier nested in each other. So this is what we mean by nested quantifiers. One more example, for every x and every y, such that, and here it says x is positive and y is negative, then the multiplication x times y is negative. So for every x and every y, if x is negative and y positive and y is negative, then the multiplication xy is negative. So this is a quantifier, nested quantifiers. Okay, now the order of quantifiers, sometimes it is important. What do I mean by sometimes? When we have nested quantifiers, universal and existential for every and there exist. If the nested quantifiers consist of both, contains both, then the order matters. But if the nested quantifiers are all of them of the same kind, universal, for example, say all of them are universal, then the order does not matter. Or if they are existential quantifiers, then the order does not matter. To make what I'm saying is clear, let's see the following example. Let x comma y denotes x plus y equals 0. And the domain here consists of real numbers. Okay? Now, in part 2 here, we just have seen it. For every x, there exists y such that x plus y equals 0, and we know this is true. Okay, what happens if we change the order of quantifiers? I mean, what happens if we move the existential to be the first and the universal to be second? So what will happen here? And this is, we answered here. Let's see what's happened. This now says for every y, for every real number. I'm sorry, forgive me. This says there exists a real number. There exists a real number. So we have the set of real numbers, and then we are saying there is one real number such that, so let me pick that real number y in hand, such that for every other real number x, we must have that x plus y equals 0. Is that true? Like if I chose a fixed real number, then is it true that if I take any real number and add it to this, I will get 0? So that's wrong. So the statement becomes false. Now, what we learned from this example, that if we change the order of quantifiers, then the meaning will be different. So changing the order, the meaning will be different. Let us see another example for that. Let q of x, y, z be the statement x plus y equals z. So we have three variables, x, y, z. We are saying here, add the first two, it must equal the third one. Okay. And let's see in this example here and this example here, what happened if we change the order of quantifiers, the nested quantifiers. Now, for this it says, for number one, says for every x and every y, there exists z such that x plus y equals z. Is that true? So if I, for any real number x and any real number y, if we add, there exists z such that z equals their addition. And this is true. So just take z to be their addition. So this statement is true. For every real number x and every real number y, there is a real number that equals their addition, which is their addition itself. Okay, now what happens if we change the order of quantifiers? What happens if we move this existential quantifier to be at the beginning here, so that we get number 2? So let's see what happened. This says for there exists z real number. So we have all the real numbers. Choose z, there exists z. So let it put it in this hand. Such that for every x and every y real numbers, x and y equals z. So there is a real number such that for every real number x, every real number y, we have x plus y equals z. Is that true? Is there a real number z such that if I take any other two real numbers x and y, then I add them, I get z, then I do it again, choose another x and y, add them, get the same z, and again? Apparently this is false. So if we see here now, what this example helps us to understand, changing the order of quantifiers has changed the truth value of the nested, of the propositions that consist of nested quantifiers. Okay, so now I just said that, but it is written here. It says if all quantifiers are universal, all of them are universal, then the order does not matter. Or if all of the quantifiers are existential, then the order does not matter. What we are saying here, if we say for every x and for every y and for every z, we have some statement, say it is q, x, y, z, then it does not matter if I change the order and say for every y, for every z, for every x, q, x, y, z, we still have these statements to be equivalent. Same thing if we have all of these quantifiers to be existential, say for every x, there exists x, there exists y, there exists c, such that q, x, f, x, y, z, it is equivalent for saying there exists z, there exists x, there exists y, same statement, q of x, y, z. So the equivalence is still happening if we change the order now. So changing the order of quantifiers does not matter. Changing the orders of quantifiers, put this here and put this here, does not matter, does not affect the truth value. Assuming the quantifiers are all of the same kind. Okay, now quantifiers of two variables. Let's have a look at this. For every x and for every y, which is the same as we just said for every y and every x, changing the order does not matter here. It says that p of x is true for every x and every y. So wherever you have a value for x or for y, p of x will be true. And here it says for every x, there exists y such that this is true. So for every x, for any x, there exists y such that p of x, y is true. In here it says that there exists x such that for every y the statement is true. And here it says there exists x such that there exists y such that p of x, y is true, which means there exists a pair of elements, x and y, so that p of x is true. So, okay. So now, let's see, next, mathematical statements can be translated into logical expressions. So we will have mathematical statements, and we want to translate them to logical expression. Let's see. In this example, the statement says the sum of two positive integers is always positive. Let's put that in logical statement using nested quantifiers. So it says the sum of two positive integers. So for all positive integers, x and y. So here what we did, we introduced the propositional variables, x and y. We have x plus y equals 0. Now we will express this in two ways. First, this way here, number one, is where we consider the domain to be all integers. All integer, positive and negative. So to say that x plus y is greater than 0, we need to specify, the problem says every two positive integers. So, and because now we are choosing x and y to be integers, they might be negative. So we need to specify that they are positive. The ones we are choosing are positive. So we will say for every x, for every y, such that x is positive and y is positive, we have the conclusion their summation is positive. Okay, now what happens if we change the domain, but this time the domain of the variables x and y consists of positive integers. So simply we will say there exists x, there exists y, such that their summation is positive. And we excluded we excluded this part and this part now. Why? Because our domain is already understood to be the set of positive integers. So when I say for every x and for every y, now it is already understood that my x and y are positive. So I don't need to mention these here. I'm circling in red. So another example, let's translate this statement. Every real number except the zero has multiplicative inverse. Multiplicative inverse of x is another number y, such that if you multiply x times y, we get 1. Okay, so let's do that. We will rewrite the statement by saying for every real number x, not 0, x is not 0, x has a multiplicative inverse, which means there exists y that we multiply by x, we get 1. So there exists y. So we will say for every x such that x is not 0, there exists y such that x times y is 1. Here we go. For every x such which is not 0, then there exists y such that x times y equals 1. Okay, so we have nested quantifiers here. Now we want to translate the opposite from a quantifier, from logical statement to a language. Okay, so to do so, first we write out the quantifiers and the predicates in the expression, what they mean. Then express this in simpler sentences. Okay, now let's look at that. The following example. Translate the statement into English. Now here, C of x means that person x has a computer. So the domain of x and y consists of all students in your school. So C of x means student x has a computer. Okay. F of x, y means x and y are friends, and they are from the school. Now, what does this statement mean? Now it says for every x, so this parentheses with purple, that comes indicates the statement that comes inside the quantifier every x. So every x, this C here means x has a computer. So every x has a computer, but here we will look at this. It says or there exists y, somebody in the school with a green parentheses, there exists y, this is green. What's the matter of that y? He has a computer and he is a friend of x. Okay, good. So let me go back to the or here and give it red. Now it says for every x, either, so this red is either and or. Either C of x or there exists y such that C of x and f of xy. So that means for every student x, either he has a computer, if not, then there exists y, another person in the school who has a computer, this is C of y, and he is a friend of x. So this statement will become every student either has a computer or has a friend who has a computer. Okay. Let's look at another example. Okay, f of AP means A and B are friends. A and B are friends. And the domain XYZ consists of all students in your school. So let's see what that statement means. Now, for there exists X, and this is the parentheses of the quantifier there exists X, such that for every Y and every Z, what's the matter of every Y and every Z? Y is a friend of X and Z is a friend of X, and Y and Z are not the same person. So there exists X, this X now here, it's somebody, such that for every Y who is a friend of X and for every Z who is a friend of X, so that Y and Z are not the same person, then what? Then not FYZ, which means Y and Z are not friends. So again, there is some person X such that for every two people, for every Y and Z, two people in the class, such that Y is a friend of X and Z a friend of X, Y and Z are not the same person, then Y and Z are not friends. So that statement means there exists a student whose friends are not friends. Okay, good. Now let us learn how to translate English sentences to logical expressions, and we will do that through examples. Let us see here. Express the statement using predicates, quantifier, and logical connectives. Okay, so if a person is a female, so we have and here. So we will have and a parent. So we will say f of x means x is a female, p of x means x is a parent. Now here it says then, so we will have this logical connective. Then this person is someone's mother. So there exists somebody such that that person is that somebody's mother. So we will say mxy means x is a mother of y. So okay, so we will say if a person, so for every person who is a female and a parent, for every person who is a female and a parent, there exists y such that that person is the mother of that y. There exists a boy such that that person is the mother of that boy, say for example. So for every person, if she is a female and she is a parent, so now you see this and here with red, it is the and above there I made. Then so if she is f of x and p of x female of parent, then there exists y such that x is a mother of y. Okay. Another example. Everyone has exactly one best friend. So we want to make that as a logical statement. So we will use p of x, y to be the statement y is the best friend of x. So every x will have one best friend. So the statement x has exactly one best friend means there exists y such that what? Y is a friend of x. Okay? such that, so there exists, so for x, we're talking for x. For that x, there exists y who's a best friend of x. How to say that? And then we will say if z is another one who's not y, then z is not the best friend of x. So there exists y such that y is the best friend of x, and for every other person who is not y, that person, which we call z, is not. So this is the negation, is not best friend of x. This is happening for a specific x. Now we want to say this happens for everybody. So we will say for every x, this is happening. And now we got every x has a best friend. Okay. Now the last part is to negate quantified statements. Now we learned before how to negate negating nested quantifiers. We have already learned that whenever we want to negate sorry. Okay, so we learned before how to negate the universal quantifier. So we say to negate negation of every x, p of x, it is we will change the quantifier and we will bring the negation to the inside. Same thing if we negate there exists x, p of x, then we bring the negation to the inside and then we change the quantifier. Okay, now what we do here, if we want to negate all that, we will bring the negation to the inside of the universal quantifier, but we change the universal quantifier to existential. Okay, so we get that. Now again, to proceed, we will move the negation to the inside of the existential quantifier, but we will change the existential to universal. So we get this. And one more time, we'll bring the negation to the inside and then change the quantifier. Then we get that. And the negation, as we see it here, is as follows. This negation brings this, and then we are done. Remember, P gives Q is equivalent to not P or Q. So to negate that, use De Morgan's law, we get this. And these are two good rules to remember. So this gives us an example on how to negate nested quantifiers. If we want to execute that example on something that we know from calculus, it says the definition of continuity says for every epsilon greater than 0 there is delta such that f of x minus L is less than epsilon whenever x minus a absolute value is less than delta, where L is the limit. So it says for every epsilon there exists delta such that for every x this is happening according to the definition of continuity. Now if we want to negate all of that, so we will repeat the process that I have just showed you, but now we will replace this with P gives Q, where this is P and this is a Q, and then follow the process of what we have just seen, and then we will end here. Okay, and this brings us to the end of this section. Thank you.